Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to pick up the topic we left off last time by talking about commutators. So we brought this up a little bit in when talking about the idea of the Heisenberg uncertainty principle. So this is again the idea that it can be impossible to measure two properties simultaneously. The most famous example, of course, being position and momentum. However, it turns out that this is going to apply to any sort of system where the operators essentially are complementary. So one way of describing complementary operators is essentially if applying operator 1 to operator 2 gives you a different answer than applying operator 2 to operator 1. However, in order to actually get some real numbers out of the system, you almost always have to apply this to a wave function to really kind of demonstrate the system. And so you can think of complementary operators as ones being in which the order of operation matter. So again, if I have a complementary operator, I can't just willy-nilly mix out around which order I work on the system. I have to very carefully follow my set of order of operations when acting upon my given wave function. And again, it is worth noting that these always are in light of operating on a wave function to really show that an operator is complementary or not. However, it's a little bit awkward to try and define complementary operators in this way. So complementary operators are often defined using what's called the commutator. So the commutator is kind of its own set of operators. So again, we'll typically use the commutator, as shown here, as essentially an operation on a wave function, where the commutator means that I'm going to apply operator 1, operator 2, followed by operator 1, minus operator 1, followed by operator 2. So if I use this commutator to act on a wave function, if I have a complementary set of operators, this is going to give me a non-zero answer. If the operators are non-complementary, so in other words, they commute, this should give me a value of 0. Now, this can be very important because if they give you an answer of 0, that means it doesn't matter which order of operations the order of operations in which I apply them on a system, which gives me a lot more mathematical flexibility. But more importantly, it also means that I can measure two properties simultaneously, which gives us a lot of real world sort of applications. And it is worth noting that the most famous set of complementary operators are, again, position and momentum. But there's also a wide world of other complementary operators out there. One of my personal favorites being energy and time. It's possible to know the exact energy of a system, but you never know exactly when you measured it. And if you know exactly what point in time the system is at, then you know nothing about the energy. And again, we're going to encounter a fair number of complementary operators as we go through the course. So it's fairly useful if we can first identify which ones don't commute and which ones do. So let's go ahead and try and apply our commutator to a real system. So who doesn't love position and momentum? We know that these two should be non-complementary. So let's go ahead and work on the system. Now, again, one of the things I do want to make note of is in order to make use of the commutator, you do always need to let it act on a wave function. So let's go ahead and apply our commutator of x and position and momentum to our general wave function psi. So when we go ahead and do this, this is going to be the same thing as taking the momentum followed by the position minus the position followed by the momentum. Now we can go ahead and put in our actual operators. X for position and the derivative of x for momentum. So the first one is actually fairly straightforward. I just have the derivative of psi with respect to x. HI should pop out front because it's a constant and I'm not taking the derivative of the system, so it's nice. The second one gets a little bit messier because here I'm now taking the derivative of x times psi. But by the very definition of the system, psi should have an x dependency. which means, congratulations, it's time for some good old-fashioned product rule. So we can then divide the system out. So I'm going to first have the derivative of keep psi constant and take the derivative of x. Well, this one's nice. It's just 1. And then I'll take the leave x constant and take the derivative of psi. And well, that's actually the same thing that I have over here. Now we have to go ahead and distribute out our negative. So subtract the system. And well, lo and behold, this first term and this third term are identical. So they'll just cancel out. However, nobody cancels out this nice middle term. So what I'm left with is a negative h bar over I times psi. Well, it's important to remember that -1 is the same as I squared. So I can replace that negative with an I squared and then let one of the i's cancel. So this is actually a fairly useful thing to know. -1 over I is going to be the same as I. It's just a useful trick I'll use now and then. So this means that the commutator applied to psi gives me I h bar times psi. So because of the nature of the system, and again, you can think of this like an eigenfunction, eigenvalue, that it turns out that psi is going to be, no matter its form, is going to be a eigenfunction of the commutator of x and px with a value of I h bar. So as a result, we generally define the commutator as, again, that eigenvalue. However, you'll note that this is I can't say a real value, but an actual numerical value, even if it is imaginary. And this has the unfortunate meaning that the commutator is not equal to 0. So position and momentum don't commute. And this is, again, how we can identify that I can't measure both of these operators simultaneously. And being able to identify when an operator commutes and doesn't is going to be a very important feature of trying to describe real systems. So this actually brings us to the end of essentially our basic quantum mechanical principles. From here on out, we're going to go ahead and spend some time dealing with real quantum mechanical systems. First, particles moving in one direction, then particles rotate, moving multiple directions, and particles rotating. And then we're going to get real funky and actually talk about chemistry. So before we do that, I want to kind of give a big summary of our quantum principles. So we can summarize our key features of quantum mechanics in kind of 4 key points. First of all, the wave function is kind of our bread and butter of quantum mechanics. So it's going to contain all the necessary information to completely define a system. However, it doesn't just scream the answer at you. It's kind of embedded in there. So we have to know how to ask it the right question. So again, while the wave function isn't real, it is going to be a perfect description of our system, as long as we know the right questions to ask. One of the simplest questions we can ask is essentially, where are you? And we use this with the Born interpretation, where essentially by integrating the square of our wave function, we can get out the probability density, or the probability the particle is at any given point. Most of the rest of our observables can essentially be generated by applying the correct operator to our relevant wave function. However, if they aren't an eigenfunction, if the wave function isn't an eigenfunction of that operator, we're likely going to have to settle for an expectation value instead. So again, this means applying the operator and then integrating overall space. It's not ideal, but it's often the case. And then finally, when we bring in the Heisenberg uncertainty principle, it essentially is going to help us identify that sometimes we can't have it all. We can't always determine 2 properties simultaneously. Sometimes I have to try and admit the fact that if I know one value perfectly, I'm not going to have any information about the other. And again, you can get some of this information by trying to actually calculate the uncertainties of the certainty of how well you know a property by doing things like calculating the variance and the exact position of a system directly using our operators. Using this, you can get the uncertainty in. You can actually find the uncertainty in position, momentum, energy, or anything else you want of the wave function you have. So next time, we're going to go ahead and return back to the free particle, this time with a little bit more knowledge. Until then, take care.